We're often interested in moving charges from one place to another because that's the basis for electricity. And it's important for us to know how much energy or how much work it takes to be able to do that, or how much energy is released when an object moves from one place to another. And so that's what we're going to focus on for this learning target. In particular, we're going to assume that we have some arrangement of charges that are fixed in space, and we're going to move an extra charge relative to those ones that are fixed. So if we want to know the work that it takes to do that, we'll just use this definition that work is equal to the change in energy. Now here the energy type that's changing is electric potential energy. And we know from before that electric potential energy is just equal to Q times the electric potential. That's the definition of electric potential, is just the ratio of electric potential energy to charge. So you can multiply those two together and get electric potential energy. If we want the change in electric potential energy, then we need the change in electric potential, or the voltage, or the potential difference. Those are all synonyms here. So our method for figuring out how much work it's going to take to move a charge from one point to another will be to find out what the potential difference between those 2 points is, or start by finding the electric potential at each point, and then find the difference of those two electric potentials. Then we just have to multiply by the amount of charge that we want to move from one location to another to figure out how much work it's going to take to do that. So, to get an idea of how this works, we'll consider this arrangement where we have kind of a square shape here, and these two charges over here are going to be fixed in place, and then charge number 3, Q3, we're going to move from point A to point B. We want to know how much work it's going to take to do that. So, first up, we need to find our electric potentials at point A and at point B, see how much that's going to change, and then we'll multiply by Q to get the amount of work done. So, the electric potential at point A is equal to the 1 over 4 pi epsilon naught, and that's got a value of 9.0 times 10 to the 9th, and the units on that are Newton meters squared per Coulomb squared, times, and now we're going to add up the charge over the distance for each of these two charges to point A. So this one we've got a charge of negative 3.0 nanocoulombs, that's times 10 to the negative 9th coulombs, over our distance, 0.25 meters, plus, and then our charge for Q1 is a positive 5.0 times 10 to the negative 9th coulombs, divided by our distance, so that'd be this diagonal distance, so we got the 0.25, we can just do that Pythagorean theorem there, and we get 0.25 times the square root of 2 meters for that one. And so our potential, electric potential at point A then, is going to be, let's see, about 19.3 volts. And then at point B, it's going to look very similar here. We'll still have the 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. And this time, that 5.0 nanocoulombs, that's going to be 0.25 meters away, and the negative 3 nanocoulombs, that's going to be the 0.25 square root of 2 meters away. So we're just flip-flopping these two charges, basically, or flip-flopping these two distances. So negative 3.0 times 10 to the negative 9th coulombs divided by 0.25 times the square root of 2 meters, plus 5.0 times 10 to the negative 9th coulombs divided by 0.25 meters. And so for the potential, electric potential at point B, we get now 103.6 volts. Now the change, we're going from 19.3 to 103.6. So to make that change, we're changing by 84.4 roughly. But it rounds up to 84.3 with what I have written here, but the unrounded value is about 84.4 volts for our potential difference, or our voltage, if you prefer. And then the work is going to be equal to the charge times the potential difference there. Our charge was 2.0 nanocoulombs. 2.0 times 10 to the negative 9th coulombs times 84.4 volts. And now we get a, we get a work required of 1.7 times 10 to the negative 7th. And work is in joules.